Today, hello everyone. Today I am going to present my homework. Uh, it it is a folded line microchip for quantitative detection topic. Myself, Selim Reza, and my student ID is 2021160207, and I'm from Electronic Engineering Department, Kangwon University, Seoul, South Korea. So basically in this topic we will cover some general overview of the folded microchip of biosensor. Basically this reusable RF reversed RF biosensor with a rectangular mandate line, which is called as RML resonator on a gallium arsenide substrate by the IPD technology was designed, fabricated, and tested, which is enabled to real-time detection of the glucose level in human serum. And another case for ER-based structure, which is fabricated also by the IPD technology and applied to the resonator, and which is improved the sensitivity of the previous one by the magnitude of the transmission of the coefficient. And resonator behavior based on the S21 characteristics of the biosensor is analyzed at 9.20 gigahertz of human serum containing the different glucose concentration ranging from 148 milligram decimal to 268 milligram per deciliter, and it also measured in 105 to 255 milligram per decimal, and deionized water also concentration range from 50 to 25 to 50 milligram per decimal for different 7 samples. And after that, the calibration also analyzed, and this calibration also was performed for the human serum from two different subjects. For the glucose deglucose with the response time which is 60 seconds, and the reproducibility, the minimum shift rate of resonance frequency, and the long-term stability signal were investigated for this RML resonator. And the feature characteristics based on the resonator concept after use the serum as an analyte are model as a inductor, capacitor, and resistor also. Basically, this RF sensing technique apply for the DNA hybridization, binding of bitin, and step division, and metamaterial and microwave glucose sensing also uses RF technique, which is most popular. And a level-free minimum invasive rectangular RML resonator functioning at a microwave frequency, which is range is 9.2 gigahertz, which is also analysis for the detection of the glucose level in the human serum, and compare with the aqueous solution of the deionized water solution. And both are the compared with each other, and the detection of this glucose level based on the variation of actually dielectric property of different concentration of the glucose present in the serum, and the changes of this electrical behavior due to the skin effect of the moderate conductive line. This dielectric property change, and also resonance frequency also change, and the sensitivity enhancement of this resonator and ER-based structure is fabricated by the IPD technology on the top of the layer of the metal, and which is improve the sensitivity by increasing the magnitude of the S21 S parameters and selective variation of the AMI's capacitance. We also before in our present previous homework we have already discussed AMI's capacitance and also AMI's capacitor, and the analyte then causes the changes of electrical behavior with the mainly due to the effect of the capacitive effect. And how this the detection is happened, the analytical concept of the detection. Basically, this analytical development of microwave resonator as a minimally invasive biosensor was performed by the using the electromagnetic solution of sonnet. And you can see the first for the view, this is the gallium arsenide substrate of the base plate, and this is the gold layer, and this is the ER bridge circuit, which is used for the sensitivity increment. This is the input terminal of RF, and this is the output terminal of RF. This is the step one, and this step two. We can just draft with a micropipette of the in the LU layer, and one milli on micro liter serum has the input here, and this RF is input, and this frequency shifted of this ER bridge circuit, and this resonance frequency is calculated by the f equal to 1 by twice by root over LCA. Here there is the ER bridge capacitance, and you can see there is a two type of losses also introduced here. I can see the return loss characteristics, and another also the first the first diagram shows the bare chip with a conductive LU top rear surface, and the second one is the 1 microliter blood with analyte and drop in the surface of the biochip, and the third one, the step 3, showing the response process after the blood is dropped and the surface return to the loss characteristics, and this is this characteristics. In another, you can see by this the concept of illustrating the current density. You can see the first paragraph, or the first diagram is the current density of AU top surface, and when the analyte is dropped into the surface of the ER bridge circuit, the surface of the biosip, and this is the whole equivalent circuit of the biosip. And this is the first the S parameters, and this is the tank circuit of the LC circuit, tank circuit. This can produce the resonance, uh, and this is the input impedance, and this is the output impedance, and this is the S21 S parameters, and this is the also S11 also another S parameter, and another this RF detections was measured, and how to fix it. We can the RF detection of the glucose level based on the resonance concept in the resonator, and this biosensor produce a reasonable shift of the resonance frequency, as well as the variation of the amplitude of the signal also you can see with the variation of the glucose concentration. And the principle of relays detection of the changes of RF signal causes by the volume of the analyte, and which is detected the dielectric parameters of the glucose molecule in the surface of the biosensor. And this biosensor was can accurately demonstrate the minimum volume of the resonance shifting for different sample of the serum and the glucose solution also. And this changes in S parameters, S21 parameters, and the resonance shift found due to the electromagnetic induction between the biosensor and the glucose with a different dielectric constants. And the measurement of the S21 and the fractional change of the resonance frequency of the resonator is monitored, this monitored. And after the first measurement of the D glucose, The structure was made with a phosphorus buffered saline PBS of pH 7 and deionizes water, and nitrogen dyeing process was then the nitrogen dyeing process was used for before the next sample is containing to different glucose concentrations analyzed. This is the this is uses for before going to the next to the procedure. And the RF detection also, the mandate line structure contain a sensitive ER-based structure with a gold on the top surface, and which is generated a capacitive effect between the serum of the surface and the above and below of the ER base. And this serum containing a different glucose concentration corresponding to the different dielectric property, and which is changes the dielectric property of shifted the resonance frequency, and this also detected by the this monitor. You can see this is the RF fixed arrangement. This is our serum. This is the input terminal, then output terminal, and this is the vector network analyzer and the symmetric diagram of the RF frequency arrangement of the glucose monitoring. And this VNA basically connected as a like as S21 and S22. This is the transmitted parameter, and this is the incident parameter. And you can see the first diagram was input as a PCB layout of this sensor, and these are the 3D view diagram of the glucose sensor with the ERB circuit, and the top layer is the AU layer. And here you can uses the 1 microliter serum, and this is the input RF frequency, and this is the output RF frequency, and the resonance shifted also here you can see. And this is also the vector analyzer machine setup for the analysis of the S parameters. And this is the ER bridge structure between the metal layer of 3D view, and this is the scanning electric microscopic SEM picture of this. Basically, this RF detection and measurement are fixing several of processes or procedure. The first was is the normal person blood uh, dropping into the AU layer as this simple like as that, and then the first RF is tested, and when the RF resonance is also measured, and the RF measure also in the data in the stored. After that, wash by the using of the PSB, which pH is 7, and then another unanalyzed blood is also put here, and the second RF test is conduct, and after that the second resonance frequency also measured, and this is the measurement 2 is data is stored. You can see this actually the experimental procedure demonstrating the measurement process of the pre-treatment process and the post-treatment process of the glucose level detection process. And the most two parameters also analyzes for the uses of the biosensor. The first is the reproducibility and the surface characterization. And the first one, you can see the Bayer, the 2D view of the Bayer biosensor. And this is the A1. A1 is as a 3D view of the this profile. And after that, this also the RF measurement of the device A2, and this is the line graph of the surface roughness. And this is also blood for using the drop end and the 2D view of sensor with a serum concentration 148 milligram per deciliter, and this is the 3D view of surface profile, and this is the line graph profile for this also measured, and this also a line profile for the surface roughness. And after the cleaning, this surfaces look like that. And the 2D view of the biosensor after the test and washes with the PBS. And this is also 3D view after the wash and the surface profile. And this is the RF measurement, CE2, the picture. And this the line profile for the surface roughness. Basically, these have some standard deviation can found it of the Bayer sensor, ST, with a human serum and the sensor after the cleaning. We can found it here, with the standard deviation. The first one is the 1.2, 1.20, and 1.92 and 1.22 are respectively for the each of the experiment. And the 2D and 3D pictured view of the Bayer sensor with a RMS value is almost 63.6 nanometer, and the resonance frequency is measured is 9.20 gigahertz. You can see in the table the comparison of the RMS value of different surface morphology determined via AFM technique for different tests of the experiment for different time. There is the bare capacitors. You can see the first test, the RMS value is 63.66 mm, and the second test is also conducted, and this is also another, and this is the third test, and the minimum average value is 64.69, and standard deviation 1.260. And these are the blood when you drop in the blood in the glucose sensor, and after that the cleaning it also like as that. So the conductivity improvement of the resonator surface reproduces a pattern with a best surface morphological structure, and argon plasma was used to adjust the surface roughness via etching, and the top surface of the resonator plate with the AU can be effectively etched by the argon plasma for generation of the good surface morphological structure. And how this RF technique, this sensor can respond. And the first response graph is here showing here. The reusability of the proposed biosensor was verified with the resonance characteristics, and after supporting by the morphological analysis, the bare chip and a chip with a blood serum, and finally a chip was washed with a PBS. And the two feature frequency was observed here. One is the bare chip resonating 9.20 gigahertz, and a chip with a deep glucose serum for diabetic patient with a different concentration was dropped. And the transmission parameters clearly reflected of the electrical behavior of the devices. You can see that there is several frequency of this mm, sensor of the resonance frequency. You can see here is the variation of the resonance frequency of the deep glucose with a minimum concentration of the glucose. All these are separated, and these are almost from say 8.6 gigahertz to 9.2 gigahertz. And this also response graph for the variation of the resonance frequency for the serum for the sample one, with a minimum concentration of 148 milligram deciliter. And this is also, you can see all the graph are distinction between each other. All the resonance frequency are plotted versus the S1 parameters, transmission coefficient, and the variation of the resonance frequency for serum with a minimum concentration, and this concentration is 105 milligram deciliter. And another parameter we also here analyzed is the essay time and how this effect for this response. Basically, this essay time is the time varying calibration curve is generated by the dropping of the 1 microliter d glucose with a concentration ranging from uh, 50 to 500 millideciliter for different time interval up to 4 to millimeter 4 up to interval 1 minute, and the device exhibit a shifting of minimum shifting of 0 microhertz to maximum shifting of 80 megahertz for the measurement of the time interval of the 4 minutes and the 1 minute respectively. And at a minimum concentration, here is also minimum concentration uses 25 millideciliter. You can see in the graph, the graph have the has own, and these are the measurement, and this is the 1 minute, and the red one is the 1 minute graph, and the green is for the 2 minute, within 2 to 3 minutes. And this is the illustration of the frequency shifting of the different measurement time period, 1, 2, 3, and 4 minutes less than. And this rapid changes an excellent result, basically with a tolerable shift rate of the resonance frequency, and these are obtained of the measurement interval of the 60 second. And this minimum glucose concentration of the 25 milligram per deciliter, which is demonstrate the enhance the real-time identification of the glucose concentration level. So from this result, we can conclude, we can take a decision. The minimum assay time around 1 minute may be appropriate for the best result for consideration of the detection of the glucose level. So the analysis for the different etching time also another important things for this resonator. Different sample of the devices for various etching time is observed, and the required output RF output signal before after serum dropping into the devices also analyzed, and the AFM figure also analyzed, which is suggested that the etching time 5 minutes produces a good morphological surface profile than the other etching time. So we can measure the output signal for the three form of devices and obtained it that the device which is each for 5 minutes produces a better result than the other devices with a no itching or itching with 10 minutes. So the correlation coefficient near the ideal value 1 was observed compared with the other also sample. And another issues to analysis the reproducibility of the devices also, and the analysis the reproducibility of the devices are subjected to the multiple iteration of the experiment also tested. And the 2 minute etching sample produces the best uh, relative standard deviation value less than 0.05%, and all the results indicate that the 2 minute etching sample may be the best candidate for the further analysis. So the data and result presented in this book, in this chapter, from the etching time 5 minutes, you can see the regressions and correlation also analysis, and the effect of an aqueous diglucose solution and the Barcelona resonance frequency devices investigated. And you can see this investigation for the D glucose. This is the resonance frequency, and these are the relative standard deviation value. And you can we can see this is the sample concentrations and for the human serum, and this is the resonance frequency for each of these, and this is the RSD, that means relative standard deviation, and this is the resonance frequency for sample 2. And this the calibration curve of the whole of these samples. The calibration curve of the D glucose and the human serum can be fitted using by the following equations. And these are the first equations for the D glucose, and these are the for the sample 1, and these are the for the sample 2. So the regression value is 0.9973 generated for the serum of sample 1 and is higher than the regression value of the sample of the serum 2. So this sample consistency is in the regression value r square value of the serum was causes by the uncertainties, the preparation of the 7 different glucose concentration level achieved from the standard deviation technique and the resonance frequency, and you can see the this regressions graph for this is the different concentration of the blood serum, and these are the standard for the resonance frequency of theirs, and this is actually the regressions and error plot for the serum of the sample 1 minimum glucose concentration uses by the 148 milligram per deciliter, and this is also another regression and error graph plot for the serum sample 2 with a minimum concentration of the glucose we uses this the concentration here uh, 105 milligram decimal, and the another graph also see you can see this is the linear and the regressions and the error plot for the D-glucose solution with a minimum glucose concentration to 25 milligram per deciliter. So the relative standard deviation and the reusability of the devices we can analyze. The reusability of the biosensor are characterized by the measuring of the resonance frequency before and after the uses of the serum and the D-glucose solution. So the total 21 different experiment of each of the sample was tested, and this presentation was presented by the scatter plot, and the no device response deorientation observed over the long iteration of the measurement process. So this is the different advantages, and the relative standard deviation which is less than 1% observed for each of the concentration of the serum sample and the aqueous solution of the D-glucose. And the observed data has no show any overlapping of the resonance frequency among the concentration of the different set of experiments, and this observation validates the proposed devices can reuse for many times after the initial uses by the using or washing by the PBS using PBS which pH is equal to 7, and the bare resonance frequency for each of the set of the experiment uh, after the washing was obtained it at 9.20 gigahertz, and which is confirm the stability and the reusability of the system. So you can see the standard deviation and the reusability graph of different sample. This is the graph 1 scatter plot presenting the sample 1, and this is for the sample 2, and each of the concentration of the glucose serum presented the value of the different successive experiment, and these are the total 42 experiment data are plotted. The indicate point indicate the minimum level of the scatter of each of the serum concentration 1.134, and standard deviation is RSD relative standard deviation is less than 1%, and this observed data exhibit no any overlapping of the resonance frequency among the concentration of the different set of experiment, and which validates the reusability of the function. Thank you to watching my presentation. Thank you.